Hello, and this is Josh Johnson on my YouTube channel with, again, everything electronic. And today I have a very interesting circuit that can perform multiplication in decimal using this wheeled counter right here. This resets the counter, and it uses an Astable flip-flop controlled by a Monostable. So you have a Monostable controlling a free-running flip-flop. So first you have your multiplicand up here. So for example, let's say we wanted to have something times 9 times something. Sorry, it's hard to focus this. You would just click the 9, as you can see. And let's say we wanted to have 9 times 5. So what we can do now is click the 5 in the upright position on this one. So this blue one is the multiplier, but it runs out at 7. So 11 and 12 are 8 and 9, and then 1 through 9 are the multiplicand. So multiplicand is red, multiplier is mostly on this blue one here, and your 555 timer based circuitry is here. So let's run it. And you can see it's doing repeated addition to perform the calculation. So the problem was, of course, we had 5 on the multiplier, and then we had 9 on the multiplicand. 9 times 5 is 45, and that's exactly what the wheeled counter shows us right here. So it's accurate. Okay, let's work one more. Let's say we wanted to have 4 times 5. So we would have 4 here on the multiplier. So you can see me trying to enter it. And then we would have 5 here. And we would have to depress the 9 back into the off position. And when we trigger the monostable flip-flop, it starts the Astable and the process begins. And the repeated addition begins. So it gives 22, so it's off by a little bit. These capacitances I'm trying to make precise. I might have to use a different timer than the 555. This is your monostable, this is your Astable. And when the monostable's triggered, this light's indicating the calculation is underway. So one last problem would be, let's just do 8 by 8, 8 times 8. So we depress 8, and then we would turn off the 5, and then we'd have to, of course, again, it's harder than it looks to trigger these, turn off the 4, and then you see it runs out at 7. So the multiplicand, or multiplicand times the multiplier's product is pin 11 up here, was designated to be efficient. So we can reset the counter and run it. Let's see what it gets. 8 times 8, which should be 64. $67, so it's off a little bit. And one final problem we could do, let's just do 8 by 5. So 8 on the multiplicand, as before, you can see the 8 switch has been that up position, the other one's down. We turn off the 8 there, and then we would go over to the 5, which would be right here. There we go. And so now we would clear this counter and we can run it again. So 8 times 5 should be 40, so let's see how close it gets. $42. So it's off by a little bit. The tolerance in these capacitances would set the RC constant is reflected in the output. So one final product would be 9 times 9. So 9 would be on the multiplier here, and of course, although it's hard to see, it would be there. Let's see how close 9 times 9 gets. You can see it's faster in this oscillation. Should be 81. Holy cow, there we go, 81. 9 times 9 is 81. So it needs some work on these RC constants, but I'll explain really quickly how this thing works. And let me give a view of the whole apparatus here. That's it. You have your power supply dual rail. 24 volts triggers the, which is both in series, triggers the counter, and of course the 12 volts run to the 555s. So it does a really complicated operation with only 2 timers and a bunch of capacitors. But this LED here is like indicating the processing is going on. So when you turn the switch over here to trigger the monostable flip-flop, which runs the Astable, the LED is on as long as it's counting. And the moment it stops counting, that LED turns off, as you can see. And so 162 is what it gave, which is 81 plus 81, which is what is expected. And of course, this one over here has an automatic clear. It has another pair of lines. But a quick explanation is in order as to how this thing works. So in effect, the monostable flip-flop gives a single pulse, which when we press the 1 key has a certain length. We'll call it L. In reality, this is 2.2520 seconds. Now, this is the monostable, which yields this. Now, when you press the key from 1, this is what you get. It doubles the length for 2, and it multiplies it by 9 by hitting the 9, and it does that via the RC constant. Now, the monostable triggers a free running, it turns on and off an Astable flip-flop, and how many pulses it gives is related to its RC constant. So during L, when you press the 1 key, it gives the 1 pulse that triggers the counter. And so for instance, if you wanted to multiply it by 1 by 2, you would use the 2 key, which would give you 2 in the same, which would be this one here and that one there, and so on all the way through here. In other words, when you hit 9, it gives 9 pulses during the 1 time L. And since this one, the multiplicand, which is the monostable, allows timing, so you can have 9 of L plus 9 pulses during L, it allows you to work multiplication. And the wheels themselves work addition, so you can do multiplication and addition using this contraption. I thought this was a very interesting circuit. It would make a good first-year circuit for a 555 timer to show what it can do, and I imagine you could make this more precise. You can see you have your polymer and capacitors here, and some ceramic ones that are being used to trim it, and that's basically it in short. I hope this was interesting. I'm going to post a schematic, and if anyone's curious, the schematic hand drawn is roughly akin to this diagram shown here. You have your monostable triggering your Astable, resistance is set the monostable, capacitance is set the Astable. The power transistor runs the counter, and that power transistor is here, monostable, Astable. And this is your multiplicand, and this is your multiplier. It's shown opposite. This is really the multiplicand, and that's really a multiplier. Anyways, I hope this was interesting, and might interest some in the mathematical ability of electrical engineering. Again, this is Josh Johnson at Georgia Southern, and all the best.